Greetings. This video is part of a series of lectures for CE235A Advanced Structural Analysis. I am Arturo Tajiroglu, professor at UCLA. The title of this presentation is Torsion of Circular Cylinders. This material is meant to serve as an introductory or review material for the more advanced topics that we're going to be covering in structural analysis. Much like the venerable Bernoulli-Euler beam theory, the torsional model rests upon a kinematic hypothesis, and the kinematic hypothesis is identical, that the plane sections remain plane. In other words, there's no warpage of the cross section when you apply the forces. Here we're looking at, on the top, a circular shaft, and let's assume that we have drawn a hypothetical grid on it with perpendicular angles between the vertical lines, the circular vertical lines, and then the horizontal lines. If we apply torque to it, the vertical lines that represent a cross section will remain a vertical line. They will not become the circle will not have a larger circular cross section or a smaller circular cross section. These circles won't warp out of their plane of deformation. The only thing that we will experience here is that those 90-degree angles of our grid lines will turn into some other angles depending on the magnitude of the forces applied. So based on this kinematic hypothesis, we're going to be doing much the same what we have done for Bernoulli-Euler beams. How is the torque related to the deformations? What is the stress distribution within a circular shaft under applied torque, etc. All of this theory is due to Charles Augustin de Coulomb, who was an 18th, 19th century mathematician. We will also, in a follow-up lecture, discuss torsion of non-circular shafts, and in those cases, the basic assumption about plane sections remaining plane will be violated, so we'll have to resort to some more advanced theory to get the solutions for those types of problems. But let us focus on the circular shafts for now. We are now looking at a circular shaft, and let us use the XYZ to denote the axial and the two cross-sectional coordinates respectively. And let us focus our attention onto a segment of this shaft of length delta x. And let us assume that we are applying a torque to this shaft of magnitude mx. Sometimes we use this little circular arrow to denote the direction of the applied mx and its magnitude, and sometimes we use the double-tipped arrows to denote the same. Let us take a closer look at the equilibrium of this little segment that I've isolated here for you. On the left-hand side of the free body diagram there, the internal torque with its positive direction is T of x. And if we have a distributed torque of magnitude little t of x along this little segment, then of course the magnitude of the internal torque will have changed to T of x plus delta x at the other far end. I'm going to then add up all these forces or torques together to evaluate the balance of angular momentum about the x-axis, i.e. the moment equilibrium. And if I do that and normalize that result, that equation by delta x, and take the limit as delta x goes to 0, forgive the equal sign in that slide after the limit, that's a typo, then I will have obtained a differential equation that expresses the moment equilibrium about the x-axis, that the first derivative of the internal torque plus the distributed torque is equal to 0 at all positions x along the length of the beam. So then the other question we have to ask is, well, if this is the equilibrium equation governing the internal torque, how is this internal torque related to stress? So for that, we need to define and explore the shear stresses, and this discussion will be analogous to our exploration of the axial stresses in the axial problem, and what distribution of shear stresses are going to be occurring within the cross section. We will have to deduce those. What is the constitutive law between the applied torque and the deformations that it causes? We also obviously have to define a metric of deformation for this problem, like we have done for the bending. There, the metric of deformation was, say, curvature, and we have related the transverse deflections in a beam to curvature. And in the axial problem, we have defined something called axial strain, and we've related that to the axial displacements. We're going to have to do something similar here with the torque problem. We're going to define the shear strain and the shear modulus, and that's also analogous to axial strain and Young's modulus in the axial problem. And we need to relate the so-called strain measure to the displacement measure for this particular problem. And that measure of deformation in the torque problem is labeled as twist, as you will see, and this is going to be analogous to the axial displacement there. So before we make any headway into that exploration, let us remind ourselves what shear stress is and how it's characterized in a given cross-section, for example. Let's say that I have a beam or a shaft or a portion of a shaft, and it is subject to transverse shear forces. If I cut a free body diagram and expose all the tractions on that cross-section, marked here as gamma, and focus on one little segment of that cross-section labeled here as delta A, and look at the tractions that are being transmitted from one end of this cut to the other end that are marked here as delta V, then I know that the shear stress is defined to be the limit of the ratio delta V over delta A as delta A is shrunk to a point. So that's the definition of point-wise definition of shear stresses, for which we sometimes or generally use the labels tau. And of course, this is to define the shear stresses, and if we have the shear stress distribution, we could also compute the resultant shear from it, and we can simply integrate tau, which has a unit of stress, with dA, and that is going to have a unit of area. So stress times area is going to give us unit of force, and if we integrate or sum all those little forcelets up across the cross section, we're going to end up with the resultant shear force. Sometimes it is possible, it is always possible to from a known distribution of shear stresses to obtain the resultant force, because we can evaluate this integral whether analytically or numerically. It does not matter, we can always do that. But it is not always possible to go from a shear stress resultant to a particular distribution of shear stresses. And sometimes we take the shortcut and simply define the stress as some sort of an average stress by dividing the shear resultant force with the area over which it acts upon. Here's a small example of that. Let's say that we have a lap splice joint and we're pulling the lap splice joint with a resultant force of P, try to pull it apart, and there's a little bit of an overlap on this. The overlap on the splice joint is LS, and let's say that it has a width of W, this joint, and of course then the area over which this resultant P transmits its value to the other side is going to be AS. And if we, from the free body diagram here, that V, that force is going to be equal to P, and if we divide P by that area, simply we're going to get the average shear stress distribution. Is this correct? Point-wise, no. If we are at the edges, we know that at those edges of the plate, of the splice joint plates, the shear stresses must go to 0, and this means that there must be some points in the middle towards the middle of the lap splice joint where the shear stress goes above this average. So as an engineer, we should be always wary about taking averages, because if we are taking averages, then we know for sure that at some points the stresses will be above this average, and those might be more critical for our design. Nevertheless, this is just a basic incursion on shear stresses. Let's just discover something a little bit more intriguing about shear stresses. So let's assume that I'm doing a hypothetical test on a shear wall or a plate, and I apply some shear force at the top of this wall or plate, and while holding its bottom fixed. Let's assume that this wall has a thickness, or plate has a thickness of T. I'm going to isolate a small segment of this wall of size delta X, delta Y, and I'm going to be focusing on a point at one corner of that at Z. Let us assume that some of that shear horizontal force that I've applied at the top of the wall is being transmitted through this little patch, and that its magnitude is delta VT. So some transverse shear force, and because it's a small segment here I'm looking at, then it's fair to call it as some delta force, like it's a small amount of force, delta VT. So this is a front view of the same segment. I've isolated and pulled it out. By top left corner, Z is there, and my dimensions delta X and delta Y are shown. Remember that the force being transmitted at the top side of this little segment was delta VT, and if I'm assuming that this segment is small enough, then I can define the shear stress there, or this resultant, to be just the shear stress that is being transmitted there times the area of this little surface, which is simply equal to T times delta X. So if this is a free body diagram of the yellow patch, then we know for sure that the force at the bottom, the shear force traction at the bottom of this little patch must be equal in magnitude and opposite in direction. So that's also going to be Vt. Then I'm going to assume that there are some shear forces that are being transmitted vertically on the right hand side, and I'm going to call it delta Vr, and I'm going to call this to be a product of tau r times the area over which that shear stress acts, which is T times delta Y. So there's that. So now I'm going to, from the balance of vertical forces, I'm going to say that the force on the left side must be delta Vr, and then I'm going to evaluate the balance of angular momentum about point Z. To do that, I'm going to take into account all the forces that have a moment arm relative to that point Z, and that is going to be delta Vr times delta X minus delta Vt times delta Y. That sum total must be equal to 0. And I can rearrange that equation to read delta Vr times delta X must be equal to delta Vt times delta Y. And I can substitute in the values of delta Vr and delta Vt from the expressions that I showed in the free body diagram. And so this tells me that tau r must be equal to tau t, that I can collectively call them as tau. So what the balance of angular momentum implied for this little patch is that if I know the shear stress acting on one side of this four-sided patch free body diagram, this means that I know the magnitudes and directions of all the other three stresses. So if the stress at the top is tau acting right, then the stress at the bottom must be tau acting left. And therefore, and also from the balance of angular momentum, that this pair of taus will try to spin the cube or patch clockwise, then I'll have to have an equal and opposite set of taus to spin it counterclockwise so that it's balanced about the z-axis. So this is an interesting discovery about the shear stress, that if you know the shear stress on one side of a patch, all the shear stresses are known all around that patch. I personally remember this by doing this. If I know, say, the tau direction on, say, top of this little patch, and it's running towards a corner, then its counter sister tau will run towards that same corner. And if the tau is running away from a corner, then its sister tau will also run away from that corner. And therefore, you can just, with knowing one tau, you can draw the entire picture of the shear stresses acting on a little patch that is in static equilibrium. So let us now relate the shear stresses that we have identified to the deformations. This is something we also know from before. This is a little element under pure shear, and it will have retained its dimensions, but it will have just warped out into a different shape. If its angle was originally 90 degrees, now it will become a new angle that is less than 90 degrees theta star. And shear strain is defined to be pi over 2 minus that angle. So this is the so-called engineering shear strain, which is twice the Lagrangian shear strain, but this is that total angle change. We can, of course, relate this to the deformations by making a simple observation that if this is a small shear strain, that gamma is therefore going to be a small angle, and that angle in radians is going to be equal to its own tangent, and then its own tangent is merely the horizontal displacement of the top left corner of this little patch divided by the length of the patch along the y direction, so it will be just delta over L. The shear stress and shear strain are related to each other through a simple constitutive law, which says that shear stress is proportional to the shear strain, and the proportionality constant is the so-called shear modulus, which is not itself an independent property of the materials, but can also be expressed as a function of, for example, Young's modulus and Poisson's ratio. Review your strength of materials textbooks to remember how this relationship, for example, was derived. So now that we have had a quick review of what the shear stresses are, how they're related to the shear strains, let us go back to the problem at hand, which is the torsion of a circular shaft. Again, I'm going to isolate a smaller segment of the circular shaft and take a closer look at it. Let's assume that the shaft has a radius of A, and it's subject to a torque of magnitude mx on its one side. And of course, it is going to have an equal and opposite internal torque on its other side so that it's in static equilibrium. I'm going to isolate a little plane section in this little segment of the circular shaft and observe its deformations due to the applied torque. So I'm going to highlight a little plane delineated by these three yellow lines, as well as the dashed line that is running across the center of the circular shaft. I'm also going to put a plus mark on the back side of this little patch, demarked by these yellow lines, and this plus mark will be made onto the side of the circular shaft, and it is going to have a 90-degree angle between its two legs before the torque is applied. And after the torque is applied, because the circular sections are remaining circular and there's no warpage, I can picture that deformation as follows. Right, so the back circle remained a circle. It rotated a certain amount, perhaps from an undeformed configuration, but that the front circle will have rotated by an additional amount. And this is what this yellow, the green line is marking, that it is showing that additional rotation that the front circle has made relative to the back circle. That angle I'm going to denote as delta phi. And of course, there's going to be a movement of the points from the yellow rim line to the green rim line. And those points are going to move larger and larger relative distances as they get closer and closer to the perimeter of the circle. And of course, if I have denoted those displacements as delta delta of r being the radial coordinate, then of course the circular movements that those points will have experienced will become zero as I reach the center of the circular shaft. I can also mark the angle that that is swept by the red line across the length of the torsional circular shaft, and I'm going to simply call that the gamma theta x, which is the shear strain angle, which is directly the shear strain that the shaft experiences at that position r across its cross section. So that this shear strain will obviously be a maximum at the surface of the shaft where I put my original cross mark at, and it will become zero at the center of the shaft. There's no shear strain in that direction, circumference theta x direction at all. We also know that, as I mentioned to you before, this delta delta of r will have its maximum value at the perimeter of the circle, as well as this shear strain angle gamma. So now we are ready to relate the displacement with the twist, and the twist here is simply the angle phi. I'll just call that the twisting angle or the twist. So I know that this line segment delta delta r can be computed by simply multiplying the twist angle with the radius at which I'm sampling this displacement r. So I measured it from the centroid of the circle using that angle, twist angle. But I can also sample that same distance by looking at another angle, the gamma angle, and if I multiply that gamma angle with delta x, the length of the segment, I will have obtained the same delta delta of r. And of course, I can, from the first expression, evaluate the delta delta at r equals a. This will have yielded the delta delta max, which is simply equal to the delta phi, the increment of the twisting angle from the back end to the front end times the radius of the circle. And also I can do the same expression by evaluating the other expression at the radius and say that delta delta max is simply also equal to gamma times delta x, or gamma max times delta x. So from the first two expressions, I can simply write that the shear strain at the surface of the circular shaft, shear strain as it varies with respect to the radius of the circular shaft is nothing other than delta phi over delta x times r by combining the two expressions, the top two expressions, by taking essentially their ratios. And that the maximum value that this expression will have will be the value evaluated at r equals a. So now I'm going to rewrite this expression by combining the two knowledges, two things that I've derived above, and say that gamma is a function of r, and that it is equal to r over a times gamma max. Right? So I just combine the two expressions together to obtain this little expression. In essence, I have taken the ratio of gamma of r with gamma max on the left-hand side, and on the right-hand side, the delta phi over delta x's have canceled, giving me just r over a, and I've rearranged that. So does this make sense to us? Yes, it does. When r is equal to 0, the shear strain, the hypothetical plus mark that I would have put at the core of the circular shaft, will be 0, changing its angle by a 0 amount. And then when r is equal to a, it will have reached the maximum amount. And from this kinematic hypothesis that we have adopted, we see that the shear strain varies linearly with respect to the radial coordinate, and obviously reaches its maximum value when r is equal to a, and gamma max itself is related to this twisting angle. If we take the limit as delta x goes to 0, it is going to be the first derivative of the twisting angle times the radius. That's going to give us the shear strain that the circular shaft would have experienced on its surface. So now that we know the shear strain distribution across the cross section, let us draw a picture of it. This was the formula that we had. So at the center, we're going to have a 0 shear strain. We're going to vary linearly towards its maximum value. So we're going to have this triangular distribution of shear strain. And of course, I can just multiply both sides of this equation by the shear modulus and obtain an expression for the shear stress. And if the shear strain is varying linearly, so will the shear stress. And its expression will be just tau equals r over a times tau max. I can draw that as well, and it's going to be another triangular distribution. I can expand this argument to any direction within the cross section, and of course that is going to give me a shear stress distribution that looks like this across the cross section. So it's kind of like a twirling set of arrows, all of which linearly vary with respect to the centroid, with respect to the radial coordinate. So from this I can compute two things. One is what is the resultant of these shear forces. Right, that would be a straight integral of the tau distribution within the cross section, and then also I can evaluate the torque that they create. So I'm going to try and answer the first question sort of in a qualitative way. If I, for example, integrated one line of those arrows, one little set of those arrows, and obtained the resultant shear force from one of them, I know that because of the distribution of the shear stresses within the cross section, on the other side there will be another set of shear stresses, they'll be diametrically opposing and canceling this one out. So this means that all of these shear stresses will be, if they were integrated across the cross section, they'll be canceling each other out, giving us a net shear force of 0, which is very good because we have created the shear stress distribution by applying a pure torque with no shear resultant force on it. So let's answer the second question. Well, how is the shear stress distribution related to the torque? For that, we need to do another integral. That integral, therefore, is if we isolate a little patch of size dA, we will have to multiply the shear stresses acting through that patch to get a little forcelet. That will be tau times dA. And then we would then multiply the distance of this force from the centroid to determine the contribution to the torque of this little forcelet. And if we sum them all up, carry out this integration over the entire cross section, we should get the torque, the resultant torque. You can carry out this integral in different ways, but before we do that, we can recognize the fact that tau itself is nothing other than tau max times r over a. And because tau max and a are constants, we can pull them outside the double integral over the area, and we will be left with this r squared dA term on the inside. This term is the so-called polar moment of inertia. It's a second moment of area, but it's a polar one that is being, in this particular case, carried out across the x-axis, and is simply denoted as J. And so this will be our then torsion formula, that the tau max is equal to mxa over J. And, well, the more general version of the torsion formula is simply tau of r is equal to mx r over J. We can just obtain this calculation, obtain this little second formula in the yellow box by plugging in the result for tau max from the red box on the bottom right corner, and that would give us the torsion formula. And the polar moment of inertia, as I mentioned earlier, is the second moment of area about the x-axis. So now that we have the torsion formula, we are able to now relate the torque to the shear stresses that it creates across the cross section. And now we need to relate the torsional rotation to the angle and the angle of twist to this problem, bring them into the picture here. We know that gamma max is equal to a times d phi over dx, which is the rate of change of the derivative of the twisting angle. If we multiply both sides of this equation by dx, we will get an increment, a value for phi that we can integrate. After we substitute in the torsion formula, we see that d phi is equal to mx over gj, and the gj is simply called as the torsional stiffness, much like EI, if you recall, was called the bending stiffness. We have mx over gj times dx, and if we integrate both sides of this equation from, say, position A along the length of the beam to the position B, we will get the increment to the twisting angle on the left-hand side of that equation, and the right-hand side is simply an integral of the torque divided by the torsional stiffness from A to B. So now that we have related the torque to the angle of twist through this expression, and we know what the torsion formula is, let us just examine some of the J values that the circular sections can take on. We know that we are looking at a full circle, but indeed Coulomb's theory is equally valid for other circular sections such as tubes. So let us also compute the J value for different cross sections as well. So if we do that calculation, if we do the double integral, we will find out that for a solid cylinder of radius A, the second moment of area is equal to pi over 2 times a to the fourth. And for a hollow cylinder, it is going to be pi over 2 times the differences in the fourth powers of the outer and inner radii. And you can also simplify this formula somewhat for thin-walled circular tubes. So if the exact formula is equal to pi over 2 times a to the fourth minus a to the fourth out minus a to the fourth in, but we can expand that out and say that it is pi over 2 times a squared out plus a squared in plus a squared out minus a squared in, which can also be expanded as a out plus a in times a out minus a in. And now if we're looking at a thin cylinder, we know that a out is almost equal to a, and we can just call it simply as a. So the first expression inside the parentheses will become 2a squared, the second one will be 2a, and their difference will be merely t. So then the whole expression can be approximated as 2 pi a squared times 2. Sometimes you see this approximation that is being used for j, but not the exact value, which is appropriate for all the thicknesses, and this approximate value is only appropriate for cross sections with t much smaller than a. We encounter such sections in aerospace structures, obviously. Okay, so let us now take a look at an example where this formula is applied. Let us assume that we have a shaft fixed on its left end with a torsional stiffness of GJ, length L, and let's say that we have an applied torque of positive T at the right end. So the twist at the tip end is simply, according to our formula, is phi L minus phi 0, and phi at x equals 0 is 0. It's fixed, so the tip and twist phi at L is merely an integral of the torsion diagram for the shaft divided by the GJ integrated from 0 to L. And since the torque across this determinate problem is simply t and constant, then the integral is quite easy to evaluate. It will be just t times L over GJ. So in this case, we can simply refer to GJ over L as a torsional spring constant, little j, so that the tip twist is equal to the applied torque at the tip divided by the stiffness, torsional stiffness of this circular shaft, little j. We can also imagine scenarios where we are attaching two shafts in series. By that I mean we apply a torque at the end, and where the two shafts meet, they share the same torque. That will be a connection in series. And we can also imagine a scenario where we attach two shafts in parallel, where, say, the two shafts meet, they share the common twisting angle phi. And of course, then for these two cases, much like we have done for the axial problem, we can imagine a composite equivalent torsional stiffness constant for the series connection and the parallel connection. And the forms of those formulas will be identical to what we have seen in the axial problem. Let us now solve a slightly different problem where we have some torque, concentrated torque applied at the interior of the shaft, as well as some distributed, albeit uniformly distributed, torque applied at another segment of it. Let's say that the torsional stiffness of the shaft across its entire length is 300,000 kip inches squared. We know that the governing equilibrium equation for the internal torque is merely dt over dx plus tau x is equal to 0. This must be valid at all positions within the shaft. We can solve this differential equation easily by, for example, dividing this torque into three segments and evaluating continuity at where these segments meet, etc. I'm going to now solve it actually graphically, which is equivalent to the algebraic solution of this differential equation. And to solve this graphically is easy for me to do in this case because the shaft is simply statically determinate. So all I need to do is first start by determining the reaction torque at the left side, which is this yellow arrow, and that is simply going to be 10, that reaction that is unknown, plus 10, plus 2 times 40, which is the length along which that uniform torque acts, is equal to 0. From that, I find out that R is minus 90 kip inches, which means that it is 90 kip inches directed to the left. So that is an equilibrium. That is a free body diagram that is in perfect equilibrium if you see it. Now I can start drawing the the torque diagram. I can start doing that by cutting slightly to the right of the 90 kip inches, and as I keep cutting, I'm going to be exposing the same amount of internal torque there until I reach 10 kip inches, at which point there's going to be a jump of magnitude 10 kip inches, and the internal torque will reduce down to 80 kip inches. And you can see that by looking at the second free body diagram I'm drawing down there. Then I can cut a free body diagram into some arbitrary location, say of length x bar, into the third segment, and include all the uniformly distributed torques up to that point, which are all 2 kips per inch. And then determine what the reaction is, internal torque is at the right hand side, and I can do that by simply evaluating the equilibrium about the x-axis, and that formula ends up being 80 minus 2 times x minus 40 kip inches. And as you can see, where x is equal to 0, where x is equal to 40, which is where the uniformly distributed torque begins, the magnitude of the internal torque is 80 kip inches as it is supposed to be. And then when x is equal to 80, which is the right end of the shaft, the formula for the green arrow gives us 80 minus 40 is 40, minus 2 times 40 is minus 80, plus 80 minus 80 is 0, so it closes up at 0. And it varies linearly, so this must be the correct formula. So now I can write the entire internal torque formula for the rod, for the shaft. It is 90 kip inches between 0 and 20, 80 kip inches between 20 and 40, and it's that linear formula between 40 and 80. I can then use this internal torque distribution to determine the tip twist relative to the fixed end. And so I will have to integrate it in 3 segments. I'll have to integrate the 90 from 0 to 20, and then integrate the 80 from 20 to 40, and then integrate that other formula from x equals 40 to 80. And if I do the little algebra, do the integration there, I'm going to end up with an answer that is 0.0167 radians. So that's how much the tip end of this shaft twists relative to the fixed end of it. And that was an easy calculation. So now I'd like to draw parallels of this discussion to the discussion we had with the axial problem, and consider the energy stored in a circular shaft under torsion. And using that, I can devise a Castigliano's theorem for the torsion problem. As before, the work is defined as force traveling over distance. So if I have a force vector, and this force vector is acting on a particle that is traversing a path from A to B, and that is marked with that red line, and if the path that it traverses has a tangent at a particular time, instance in time as du, then simply the work done is the inner product of that vector f with du integrated over the entire path. And if I'm looking at an elastic problem, then all the work that carried out by the conservative external agents will be stored as strain energy inside the system. So if I apply all the torsion concentrated or distributed torques on a shaft, they will then increase the internal strain energy of that shaft by the amount of the work that they have done through those deformations. So for that, I need to take I need to be able to determine how to compute the internal stored energy under pure shear. So under pure shear, I will be looking at cubes that make up my material, and all those cubes will have a single component of stress, tau. There won't be any direct stresses, no sigma xx's, no sigma yy's. And if I'm just looking at a uniaxial torsion problem, uniaxial shear stresses, then there'll be only one component of shear stresses, which is what we're experiencing in a circular shaft. We only have the cross-sectional shear stress acting, and there are no other shear stresses in the shaft. So then the energy, the strain energy stored inside this little cube is going to be merely tau times d gamma, evaluated from 0 to gamma, which is the final deformed configuration of that little cube. And because this is a cubelet, that tiny cube that makes up the shaft, this must be not the total energy U, it should be rather the energy per unit volume, so it's going to be du dv. Before we make any progress towards integrating this energy over the volume, let us make the observation that tau itself is nothing other than gamma times g, and if we integrate the work that done by tau, is just going to be half of g gamma squared. Now we're ready to do the volume integral, so we multiply both sides of that expression by dv to obtain an expression for du, and we can re-express in different formats. For example, we can re-express that right-hand side that we will end up integrating over the volume in terms of purely the shear stress by recognizing the fact that g times gamma squared is equal to g squared gamma squared divided by g, and g squared gamma squared is merely tau squared, so we can write it equivalently as a half tau squared over g dv. So let us integrate this then over the volume to get the total energy stored in a shaft across its length. That's a volume integral, so we pull the half to the front. It does not, it's a constant, and we have two integrals, one from 0 to L over the length of the beam over dx, and another over the cross section gamma of dy dz, which is dA. So then we can also pull out the g from this integral, and also recognize the fact that nothing else in this integral depends on x. So the outer integral simply gives us an L. We end up with L over 2g and an integral of tau squared dA to carry out. And tau squared dA is merely our torsion formula squared, so it's just going to be mx r over j squared. And then we can carry out some of those squares and move out the constants from the integral outside to the integral sign. Then we will end up with mx times L over 2gj squared times r squared dA integrated over the cross section, which itself is nothing other than j. So therefore, it is merely a half of mx L over gj, or you can write it as torque. If it's just an end-loaded shaft, it's just torque squared over J. So this is some formula that looks analogous to what we have obtained for the axial problem. Of course, if your problem is more complex than a merely end-loaded shaft, the final formula that we're obtaining here is not valid. You have to go back to the integral towards the left and carry out the integral of mx, the internal torque, more carefully as it varies through the cross section. Now that we know how to compute the internal energy, we can use it as part of a Castigliano's theorem. For example, if we have a statically indeterminate shaft, and this shaft is made up of, for example, two segments. One segment G1, J1 is the torsional stiffness. The other segment is G2, J2 is the torsional stiffness. And say we have applied a torque at the middle. And of course, we have two unknown reactions, but we have only one equilibrium, namely a moment equilibrium equation about x. So we're short of one equation. So this is a system that has a degree of static indeterminacy of 1. To apply the Castigliano's theorem, we need to release an adequate number of degrees of freedom to obtain a statically determinate version of the structure. So let us release the reaction on the right-hand side. And in this version of the structure, which I will again label as primary structure, I will apply the external loads. Whatever I have here, I have only one applied external load, so I'll put that back in. And so this is one instance of the original problem. And now in the next instance, I'm going to put back on the unknown reaction that the original structure would have experienced, tau b. And of course, then if I can superpose these two to obtain, I can then obtain the original structure. Then I will use Castigliano's second theorem to say that under this applied torque T, the twist at the right end, point B, must be equal to 0. I can do that by evaluating the internal energy with respect to tau b, and that should give me the twist at that location. And if I know that it is to be equal to 0, that is going to be a second equation that I can add to my nominal equilibrium equation. So this will then become a determinate problem. So in the first instance, the internal torque is easy to find. It's just tau all the way up to point C and 0 after that. And in the second problem, it is purely constant TB across the entire length. And these two problems are easy to solve by definition because they are determinate problems themselves. So then all I need to do is just superpose these internal torques and then obtain the internal energy from after the superposition for the entire beam. So the internal energy will be then a function of T and TB, one of which is unknown. T is a data for the problem, but TB is an unknown of the problem. And it's just simply a half of T plus TB squared over J1, which is the first segment of the beam. That's how much torque it has, T plus TB. And then the second portion has only TB, so that's the internal energy for that segment is a half of TB squared over J2. And if I differentiate that result with respect to TB and set it equal to 0, I then obtain a second equation besides the equilibrium equation I would have. So this then tells me this derivative is simply T plus TB over J1 plus TB over J2 is equal to 0, and that TB is equal to minus J2 over J1 plus J2 times T. And so this allows me to determine that unknown reaction. And now I know TB, this means that I know all the forces, all the internal torques across the entire length of the rod. And if I wanted to, for example, determine the relative twist between points B and C, I then have to integrate delta phi from C to B. In other words, I would have to integrate the torque diagram from x equals L1 to L1 plus L2. And the torque diagram in those segments is simple, it's merely TB. And so since I know what TB is in terms of T, I can plug it in and obtain that result. And this therefore then tells us that phi C is equal to just simply T over J1 plus J2. So this then tells us that the torque in the middle that we have applied produces a twisting angle that is governed by this relationship, and this tells us that these two shafts are connected, in fact, in parallel with each other, such that their torsional stiffnesses are added, gives us the torsional stiffness of the shaft at the middle of the shaft. So that ends our first segment of the discussion on torsion. The next discussion will focus on torsion of non-circular shafts.